I'll just start class. So everyone, welcome. Happy Friday. We'll have another of our lectures here. So let's do some housekeeping announcements first and foremost. Today is February 19th. So some things off the top of my head. Next Friday your homework is due. So homework 13 due next Friday. Just scan a picture to show that you did the homework problems, and I'll give you 10 points. And that's next Friday. I believe next Friday is the 26th. Start working on quiz number 2, as that will approach, that test will approach us sooner rather than later. So test 2, quiz 2, so work on quiz 2. A lab report for those of you that did the lab last Friday. I know I was away on a meeting, so if you want to turn in that lab report next Friday, or if you did it and you want to turn it in today, that's also very good. But the lab report on freezing point depression, we'll make it due next Friday for everyone. Right, so you still have an opportunity to do the lab after today's class. I'll be in. I have no meetings planned, so you can do the lab. I think Larissa will always be there. I'm going to be there, and I think my assistant will also be there. So please take the opportunity to do this lab with us. Whatever you choose, the lab report for this is going to be due on next Friday. And if those of you that signed up and paid money to do the clutch prep, make sure you continue to do that. Don't fall behind on those drills that I set up with that company, and watch the video tutorials as well. Alright, so I'll give you some extra credit if you complete everything from A to Z at the end of the term. Alright, so these are the only things that I see. Anything else that people can think of? All right, lab reports, quizzes. We'll have a new lab next Friday, and that's on rates of reaction. That new lab will be next Friday, so a lot happening on Friday, next Friday. Okay, homework. Continually work on your quiz, lab report due, and you guys will do another lab next Friday. Should be an interesting lab. You may like it. Rates of reaction, rate laws. It actually coincides well with what we did on Wednesday and Monday's class. So let's just go ahead and finish up as much as we can today before we head off for the weekend, or head off to the lab if you're going to attend lab. Here are some problems that involve decay. All right, so remember our key point here. If we have a reaction, okay, A goes to B, or any reaction for that matter. Okay, how do we measure how fast the reaction is going? How do we measure how fast the reaction is going? Sorry?
How much A?
Yeah, how much A is going to be. If we want to measure how fast that conversion is going, exactly correct. We do so by looking at the decay of A. Okay, so here's time. Anytime we talk about how fast, there has to be some sort of time component. And then here on the y-axis is concentration. Usually our concentration is in molar. Not all the time, but molar. And these brackets represent moles over liter, big M. Right, so this is how we measure how fast a reaction is going, by the decay of A. So the word here is decay. Decay of A. Obviously, as A decays, what else increases? Okay. B, our product will increase. But we're measuring how fast everything is going by this decay of reactant A. Right, so this decay is measured by what's called a rate law. So it's going to be rate is equal to some rate constant, lowercase k, times the initial concentration of A, raised to some power. So I'll call it x. So this rate constant is something we will have to find, or it will be given to us in the problem. The concentration in moles per liter, concentration. Have more starting off with, maybe you can get more product. Just like if you have more ingredients, you can make more cake or more whatever it is that you need to make. And then this little exponent x is called the order of the reactant, okay, the order of decay. So it could be zero order decay, it could be first order decay, or it could be second order decay. Zero, first, or second. Okay. So depending upon whether it's zero order, first order, or second order decay, we use the corresponding equations. Here's the decay for first and second order. They look alike, really. They look alike, the decay. So we do a linear transform. If it's first order decay for the reactant, we get a line if we take the natural log of the concentration. If it's second order decay, we get a line if we plot the reciprocal of the concentration over time. Remember, rates imply how fast, so obviously there needs to be a time component to it. So both of these are what's called a linear transform, because a straight line is y equals mx plus b, and the math is easy that way. So these are the equations that we will use to solve these types of problems that I'm going to show you now. One thing I also want to tell you is we can use this for your exam. So have this sheet by your side. You do not need to memorize these equations, so you want to look at them and consult them when needed. Second thing is, don't forget half-life. All right, so half-life is the time. It's a time when 50% goes away. And if it's zero order, okay, here's the equation. Funny that in a first order decay, it doesn't matter. Okay, it does not matter how much your starting material is. You can have this much, you have the whole world in your hands. You can have just a little bit in your hands. If that's going to decay with first order kinetics, it doesn't matter how much. Okay, it's just a natural log of 2 over rate constant k. So really what matters is k, the rate constant. And then finally, if it's second order, this is the equation. Okay, another big thing is the units. This is where I've seen in my experience here as a teacher that a lot of students get their units wrong. So remember, k is a rate constant, and lowercase k has to have the appropriate units. The units vary. Okay, the units will change. The units will change depending whether it's zero order, first order, or second order. Likewise, we can do the exact same thing. Okay, not all reactions are A goes to B, right? Some reactions can be A plus B goes to C plus D. Okay, here it's the same thing, but this time the rate, how fast this particular reaction will proceed, I still have that rate constant K. It's how much concentration of A you start off with raised to its order, 0, first or second order decay, times the concentration of B raised to its decay. It can also be 0 first or second order. So these x and y exponents we have to find in our, doing math. And k is something we also have to find the rate constants. All right, so that's a kind of a quick overview, a little bit of a quick overview. Let's go ahead and do some problems here. All right, let's do this together. All right, the reaction 2A goes to B is first order with respect to A. Okay, first order. Okay, so that's I'll highlight that. With respect to A with a rate constant of 2.8 times 10 to the times 10 inverse seconds. 2.8 times 10. So here at 80 degrees C. How long in seconds will it take for A to decrease? Okay, we always measure how fast a reaction goes by the decay. Okay, by the decay. And we decay starting from 0.88 big M to 0.14 big M. All right, so here's our rate constant, lowercase k. And it seems to be, it's 2.8 times 10 inverse seconds. I'll call that 28 over seconds. And it's at 80 degrees. Okay, so remember when I told you vapor pressure? Okay, vapor pressure is quoted at what? A specific temperature. So same thing here. We're going to have that same rule apply, and rate constant lowercase k will be quoted at a specific temperature. Quoted at a specific temperature. Such that if you raise the temperature, your rate constant for this reaction will change. If you decrease the temperature, this rate constant value will change. So just like vapor pressure, as we've learned before, it's quoted at a specific temperature. All right, so it's first order. So one thing I want you guys to do is look at your equation sheet here. First order, okay, here's the equation we will use. You can also use this one, okay, but I'm going to use this equation. It's just a matter of preference, but I'll use this one in red. So let's write this down. Natural log of A. Why am I using this one? Because it's first order, and this reaction has a first order rate constant. So rewriting this equation, it's natural log of A concentration equals natural log of initial AO minus KT. Right. Okay, what is lowercase t here? Is it temperature? No, it's time. Okay, time. What's this A naught mean? It means initially. Initially. So initially we're at 0.88. And then finally we are at 0.14. Okay, so kind of like our little drawing here, 0.88, 0.14 M. How long will this take? How long will this take for this reaction to proceed to go from here to here? So A sub naught, initial, is 0.88 big M. Let's start Let's start plugging in numbers. Natural log of A here is 0.14. So I don't know if you know this, but any math majors or guys taking high math classes, you don't put units inside the log. You don't put units inside the natural log. That's just a math something something. Okay, math rule. All right, natural log 0.14. So obviously we put the units at the end of our answer. Initial concentration here is 0.88. Minus K, 2.8 times 10 inverse seconds is 28 over seconds. And we were asked to find lowercase t time. Okay, so we need to solve for this. Okay, so let's solve for t. So let's move this to this side of the equation. Natural log of 0.14 minus natural log of 0.88 equals minus 28 over seconds times t. Okay, we have to solve for t. Natural log of 0.14 minus natural log of 0.88. Let's do that on our calculator. Natural log of 0.14 minus natural log of 0.88 minus, let's do this here, minus natural log of 0.88 minus 1.838. Let's put an extra digit there, minus 1.8383. Alright, equals minus 28 inverse seconds times t. Alright, so let's just cross multiply to isolate our t. So we will get minus 1.8. Oh, I'm sorry here. Minus 1.8383 seconds divided by minus 28 should give us t in seconds. Okay, the minus and minuses cancel. Minus 1.383 divided by minus 28. Like I said, the minuses cancel. 0.0656 seconds. 0.065, maybe we'll do 7 seconds. 0.0657 seconds. Actually, since these numbers were in 2 sig figs, I'll just make it 2 sig figs and we'll make it 0.066 seconds. 2 significant digits. So that's really small. I can multiply this by 1,000 and get 66 milliseconds. Okay, same thing. All right. And that's our answer. So it takes 66 milliseconds for this decay to happen. Okay, and first order kinetics. 66 milliseconds to go from here down to there, to go from 0.88 molar to 0.14 molar. Remember, molar is moles over liter. So these are the type of problems that you'll see in your homeworks and quizzes, and also our second test. We good? All right, so here are some equations, and this is basically stuff that you can read on your own during your studying. You know, again, what's really weird about first order decay is, look at here, okay, your half-life has no concentration term. Okay, this is for first order decay. we're talking about half-life here, so it's going to be the natural log of 2 over k. So they give you k, you should be able to get the half-life provided that it's a first order decay. Okay, I don't know what substances have first order decay. Don't quote me on this, but I want to say some of these radioactive things like uranium and plutonium, I think they're first order decay, so it doesn't matter how much uranium there is. Only it will have the same amount of decay, whether you have a lot or a little. So first order. Okay, also there's zero order and second order as well. So all of those equations will be given. You can use this sheet, once again, use this sheet on the exam. Those of you watching online, use this sheet for your exam. Right, how about this problem? Calculate the half-life of N2O5. Its decomposition has a first-order rate constant of 5.4 times 10 to the minus 4 inverse seconds to the minus 1. So things that you should highlight is first order. And they're asking you for the half-life. Half-life is a time, so, and they give you the rate constant. So this is a pretty simple problem, in all honesty. First order rate constant, 5.4 times 10 to the minus 4. So half-life for first order decay, again, let's use our little cheat sheet here. Half-life for first order decay is natural log of 2 divided by rate constant. All right, rate constant they give us in this problem is 5.4 times 10 to the minus 4 inverse seconds. Okay, that's seconds to the minus 1. If I flip it to the numerator, it becomes seconds. Seconds to the minus 1. If I flip it, it goes becomes seconds once I place it in the numerator, and 0.693 is part of this equation here. So my final units are going to be in seconds. Okay, remember, half-life is a time. This is another thing I've seen in my experience that students miss. When they say half-life, you have to have units of time. Okay, minutes, seconds, hours, days, even years. Plutonium, uranium, all this radioactive stuff, they have half-lives in the years, or decades, maybe even centuries. Okay, it's a time. Half-life is a time. So make sure your units corroborate that it's a time. So on our calculator, 0.693 divided by 5.4 exponent minus 4, close the parentheses, 1,283 seconds. Okay, is that something you got, Joshua? Okay, 1,283 seconds. So we can actually convert that to minutes. 1 minute is 60 seconds, so divide by 60, 21.4 minutes. So what does this answer mean? It means it takes 21.4 minutes for 50% of N2O5 to whoosh, go away. Okay, that's how long it takes. 21.4 minutes or 1,283 seconds for 50% of N2O5 to decay or disappear. So that's really the meaning of this problem. All right. Let's move on to our next problem here. Our next problem is a second order decay. So let's do some of that, a second order decay. So here's some material that you can read. To get a second order decay, to get this line, we have to take the inverse. Okay, we have to take the inverse. That's part of our linear transform. We take the inverse. And here's the equation for the half-life. Okay, notice here we have a concentration term. In the first order, we did not have a concentration term, remember? All right. The reaction 2A goes to B is second order. So what do we need to is second order. And they give us the rate constant here, K of 51, m to the minus 1 times minutes to the minus 1. I'll just move it to the denominator. It's the same thing. Notice I have a time here. The time here is in minutes. It does not always have to be in seconds, right? Calculate starting material. Starting material is 0.0092 molar. How long will it take for its concentration to reach 3.7 times 10 to the minus 3 molar? All right, let's start with part A. Let's use our little cheat sheet here for second order decay. Tell us it's second order. So they tell us it's second order, so here's the equation we'll use for second order right here. All right, so let's write that down here and plug stuff in. The equation here is 1 over A, 1 over the concentration of A is equal to 1 over the initial concentration plus KT. Okay, what is lowercase t here? Okay, it's time. Okay, so even though rate constant is quoted at a specific temperature, rate constant lowercase k is quoted at a specific temperature. This lowercase t here is time. All right, let's plug stuff in here. 1 divided by A here is 3.7 times 10 to the minus 3. So that's 0.0037 big M. Equals 1 over initial. Initial here is 0.0092. Big M plus K. K here is 51. Let's move this to the denominator and move this to the denominator. Big M times minutes, and all of that is multiplied by T. Okay, so we will solve for T now. Time T. So we have 1 divided by 0.0037 big M minus, okay, I'm going to move this to the other side, 1 over 0.0092 big M equals 51 big M times minutes times T. right, everyone with me on that algebra? Okay, good. Let's do this on our calculator. Okay, it's a little tricky here. 1 divided by 0.0037 is that, oh, sorry, let's do this again. 1 divided by 0.0037 is that, minus, here I'm going to put my parentheses, minus 1 over 0.0092. Okay, don't forget to close the parentheses. 161.575. I'll add some extra digits here. The big M stays in the denominator. Okay, that equals to 51 M times minute times t. So we can cross multiply to get our lowercase t time. So let's do that. Cross this, cross this. By the way, the big M cancels when you, those units cancel when you do the cross multiplication. So we're getting 161.575 minutes divided by 51 is equal to t, which is our time. And this is going to equal to 161.575 divide this by 51, 3.17 minutes. 3.17 minutes. I'm waiting for confirmation, but no confirmation. I think 3.17 minutes is the right answer. Right, so what does this mean? It means it takes 3.17 minutes for A to go from 0.0092 to 0.0037, right? 0092 molar to 0.0037 molar. And that's what it means. Second order decay, we use the appropriate second order decay equation. Okay. All right, let's solve for part B here. Let's do it here. We're asked to find the half-life. So here's the equation for the half-life for a second order reaction. So our half-life here is going to be 1 over K. 1 over K, which is 51 m to the minus 1. Let's move it up to the numerator to make it m. So 51 m times a minute. Okay, since it's minus 1, I moved it up to the numerator to make it plus 1. 1 over 51 times the initial concentration. The initial concentration here is 0.0092 molar. And here the big M and big M cancel. Moles over liter cancels with moles over liter. We're left with minutes. So let's see what's on our calculator here. 1 divided by 51 times 0.0092, close those parentheses, 2.13 minutes. Yes? So in 2.13 minutes, 50% of A is gone, decomposed, or gets converted to B. Okay. That's in essence the definition of half-life. 2.13 minutes, 50% of A, whatever you started out with, 50% of A has gone into the conversion of B. Okay, 50% because that's the definition of half-life. All right, any questions or comments? Bless you, bless you. Here's our final little note about zero-order reactions. Zero-order reactions just straight up form a line, right? No linear transformation necessary for a zero-order reaction. And here's the formula for the half-life. Again, you can access that for your exam. And here's a rundown, a review of all the different equations. Okay, so this is for the reaction A goes to B. And just as a reminder, in your first order half-life, there's no initial concentration. Okay, starting material doesn't matter. I'll just write here, initial concentration does not matter for first order decay. All right, something new here. I want to talk to you guys about activation energy. Activation energy, how do I put this? It's like a hump. Okay. When I say hump, not the thing that's on top of a camel. It's sort of like a barrier. Okay, a barrier. All right, so it's hard to give examples, but here's one example. I think all of you are young, so none of you have children, okay? But if you have a toddler and you try to put a... do you have a child?
No. No.
You sound like a relief.
Yeah.
No, yeah. I'm with you, Connor. Totally with you. Okay. Let's say you have a toddler and you want to put on a sweater. Okay, put on a sweater on a toddler. So how will you do that? I don't know how you would do that, but how would I do that in terms of activation energy? You have to put it on. I don't know how I'm going to draw this. You have to put it on. Okay, now will it go on so easy? Do you have any nephews, cousins, anybody who are children?
Yeah.
Okay. Putting it on, okay, it's not so easy as just, you and I putting on a sweater. There's going to be a stage where you have to just basically they're going to wrestle you and fight with you and push and turn and twist or move around. That is a barrier. Okay, till finally you can see it kind of moving around. Okay, moving its head, won't put its arm in the sleeve until finally you get the child happily in its sweater. Here it's kind of like, and here it's like, what's going on? Here it's like, sort of wrestling with you, okay, wrestling with you. So at this stage, when you're trying to get it on, when you're wrestling to put that sweater or whatever clothing on a toddler, okay, that's a hump, okay, that's a lot of energy that you have to exert. Okay, we're going to call that an activation energy. If that analogy doesn't make much sense to you, you basically look for something that is the highest point on the graph. The highest point on the graph is called the activation energy. Highest point on the graph. And putting a sweater to a child who's, very rambunctious, it's literally putting it on. Okay, trying to get the arm in, and then the other arm in, and then putting the thing down before they pull it back up, right? All those things. Finally, when the situation is over, okay, the task is over, you have a child with a sweater. Here, you have a child trying to put on a sweater, or you trying to put on a sweater to the child. Okay, that's a hump. That's an activation energy. That's a barrier to get to where you want to be. Okay, a fully clothed and warm child. All right. So, in essence, it's something you must overcome. Okay, it's something you must overcome. For a reaction, the activation energy is whatever energy it must overcome. It must overcome to get to products. Okay, so let's look at this idea of activation energy a little bit further in the last 5 minutes or so. Here we have a reaction. Okay. So here we have two reactants. Okay, I'll just call them A, and I'll call this one B. Okay. You see, A and B don't just happily form A and B don't just happily form CO2 and NO. It doesn't so happen so easily like that. Okay, you see A has to collide with B. Even then, it doesn't happen so easily like that. Okay, A and B must collide, yes, but they must collide properly. Okay, they must collide properly. Okay, so there's two things here that are going on. They must collide properly. Okay, and they must collide with the right geometry. Okay, so this is a collision, but it's ineffective. Why is it ineffective? Wrong geometry. Okay, this is the right collision, and it has to be enough so that you can get the products. Remember, these are molecules. Molecules have a three-dimensional shape, and molecules have a three-dimensional geometry. So the geometry must come together. They must be complementary to one another. Then and only then can you have a successful reaction. No successful reaction without a successful collision, without a successful interaction. All right? So it has to be this: right geometry, right orientation, all of that stuff. So all these different types of molecules, all these different types of CO molecules and NO2 molecules, only those that go like this will give you the products. Anything that goes like this, anything that goes like that, anything that goes like this, anything that goes like that, okay, you don't get the products. Okay, we want successful reactions in chemistry. By the way, all these different motions, they can be rotational motion. Okay, translational motion, that's a molecule kind of moving like this. Okay, all of this is called tumbling, by the way. We can measure tumbling in the instrument called an NMR, nuclear magnetic resonance. That's one way you measure tumbling, molecular tumbling, rotation, how fast the molecule rotates, so on and so forth. The molecules must have the proper kinetic energy. Okay, they must have the proper speed. They can't be like this. They got to be like this. Okay, so all of those things take a certain input. All of those things take a certain impetus, and we will collectively call that activation energy, the hump. All right. So what we have here on our next page, page 15, is an energy profile. This is called a reaction coordinate diagram or energy profile. So here we have A plus B goes to C plus D. Before A plus B goes to C plus D, you have to overcome the hump. Okay, that hump here is the activation energy EA. The units of this are going to be in joules per mole or kilojoules per mole. It's an energy. Okay, after all, at the end of the day, it's an energy. All right, here we have our reactants. Okay, A plus B. Okay, we got to get A and B like this, not like this, not like that, not like this, not like that. Okay, just like this. Only then the correct and right orientation, the right geometry. This is called a transition state. The right orientation, the right geometry, the right kinetic energy. Okay. Once you overcome that transition state, once you overcome that barrier, boom, we have successfully made our products. So activation energy is the hump. By the way, this is called an exothermic reaction, what you see on the left-hand side, because our products are of a lower energy. Okay, so where does all of this energy go? It goes to the surroundings. Okay, so it's an exothermic reaction. The products are of a lower energy, so that energy gap is released. Excess energy is released. Right, same thing here for an endothermic reaction. We have to overcome activation energy EA. Here's our transition state. Once again, same thing. Right geometry, right orientation, right kinetic energy, right speed, right everything. Once everything happens, we make our products. In this particular scenario, the products happen to be a little bit higher. This is the opposite. A little bit higher in energy. And this is called an endothermic reaction. So here you need to supply this energy. You need to supply the energy. The surroundings need to supply it. You need to supply it. Something needs to supply it. So here you need to supply the energy. That's endothermic, within. Endo means within. And here this is energy released. Exo means outside. Exothermic, energy released. So endothermic, exothermic reaction, both of them must overcome activation energy, which is the hump. Okay, the hump, right orientation, right speed, right geometry, right everything. Once that happens, you have a successful transition state, and then you make your products. Now you can make it with energy input, or you can make it with energy output. Okay, this is the energy profile if energy is released, exothermic. This is it when it's endothermic energy is required. All right, so we will finish this chapter up next week. Have a good weekend and stay safe. We still have a pandemic going on. And I'll see you in the lab if you have not attended the lab last week. If you have attended the lab, turn in your lab report. I think if you can, turn it in today. If not, you can turn it in next Friday.